Here we go. Good morning, ladies and gentlemen. Welcome to the fourth lecture of our course. So we are done with dry technical stuff. We have learned about creation and annihilation apparatus as a proper tool to understand advanced quantum mechanics. And we start with examples. And these examples will come from, at the moment, from solid state physics. So today we talk about magnetism, about electrons in metals, which at a sufficiently big interaction supposed to form a new state, magnetic state. Right, so I will start just talking in general about why at all I'm talking about condensed matter systems. What is the catch? Right, then we will recall non-interacting electron gas. Surely you got it in your solid state physics course. What are the metals with Fermi surface? We will refresh all this. And then we go to magnetism. We will add interaction. And here we would immediately stumble upon a major block of advanced quantum mechanics. In fact, most interesting and simple Hamiltonians, which come in advanced quantum mechanics, are impossible to treat exactly. And even numerically, and whatever, it's tediously difficult to understand the behavior, even in qualitative terms. But there's no, obstacle for willing hard. Of course, people proceed, people invent different methods, and we will eventually use immediately one of such methods, the methods of trial wave functions. Okay, after this, and we proceed with calculation, with understanding magnetic state, we will compute kinetic energy, which is going to be simple. We will address interaction energy, and that will take some story. Also, we will exercise a bit with real computation involving creation and annihilation operators. Good. Then we will understand what is magnetic state, how does it arise, how to describe it. We also understand that, magnetic axis can be rotated. And that's interesting. In magnets, there are usual single particle excitations. Like in a magnet, there are usual single particle excitations, like you have in this metal. There are also electron hole pairs. But in addition to that, owing to broken symmetry and the possibility to rotate magnetic state without changing energy, there are special excitations, new particles, magnons. And we discuss that. Fine. Again, I do like questions in the chat, and if it's not answered, you can speak up. Right. So, any feedback would be appreciated. Right. So let me just understand the problem from a bit philosophical point of view. Many courses of advanced quantum mechanics immediately go to elementary particles, to fundamental fields which we have everywhere at each point of our universe: electrons, neutrons, protons, more sophisticated elementary particles, which arise, as we know, because of presence of quantum fields. Right, we could study that, but frankly, it is a bit boring. Because what we're interested in is it's one vacuum in all points of our universe, and vacuum is empty space. Although, of course, it has potential for creating excitations. And it is much more interesting to turn our attention to the systems of condensed matter physics. What's condensed matter? It's a system of atoms, electrons. Electrons come together as many identical particles over there. And what is happening over there? Every condensed matter system, every material has a ground state. And that, if you wish, is a new vacuum. So if we accept this point of view, any new material which we create, whatever, produce, study, is a universe in its own, right? Properties of this vector can vary. Excitations at the background of this vacuum can vary, giving rise to a spectrum of different physical properties. There are metals, there are insulators, there are magnets, there are superconductors, which we will address in a week, and many various systems. I don't want to list all them. One of the easiest ways to get interesting stuff is to concentrate on unusual vacuum, unusual ground states, which come about a broken symmetry, right? Our vacuum, which we look around, seem to be very symmetric, although there are some theoretical arguments that perhaps it is not, that perhaps it's also spontaneous symmetry breaking. But with solid states, it's easy to get ground state which is less symmetric. So this is called broken symmetry. Magnet is one of these examples. Magnet has magnetization, which, as you know, is related to orientation of all electron spins along a certain axis. Good. That sets the goal for coming to lectures. The goal is perhaps rather technical. We want to see second quantization at work. How does it work? With concrete examples. And it's better to take systems which are known to you, either from solid state course or from whatever general practice. And of course, we do not want to go too much into detail. Since our examples, we keep the models which we use as simple as possible. Fine. All right, that was a philosophical introduction. Let me become more concrete and perhaps even boring, because it concerns to something which I hope at least you know by heart. Let us talk about metals. So what is the most proper and simplest model to describe a metal? It's a model which I get in the title of this slide, a model of non-interacting Fermi gas. Right, so there are fermions and they're kind of in a vacuum, to be precise, in a box which is provided by all protons in metal, but we assume there's no periodic potential. Fine. Under these circumstances, each electron, provided it doesn't interact with the brothers, just assumes a plane wave state. So the levels of single particle excitations are plane waves characterized by wave vector k. And of course, fermions, since they have spin, spin will be, for a change, very important for us in this lecture. Fine. What's the energy? In solid states, there are different spectra, because various spectros, because periodic potential can substantially modify the spectrum, can make it very anisotropic. But anyway, parabolic spectrum, simplest spectrum, would suffice for our today's work. Fine, sir, this parabolic spectrum, I kind of sketch it in this figure. Right. And let's see what is the ground state of the system. So the ground state of the system with lowest energy. Good. Well, formally, if we allow for any electron numbers in our metal, ground state would correspond to zero filling of all the levels. Energy will be zero. But that doesn't work. It's not practical. If you define metal in such a way, it's not a metal. One has to take into account that there are some electrons, some electron density per number of electrons per unit volume, which you have to put into the metal. In realistic situations, this number of electrons is just determined by valence of certain metal, certain number of electrons per atom. Good. Then let us see, what is the ground state? To house a certain number of electrons, one has to make them occupy all levels before all levels below certain energy, which is called Fermi energy. So how to see that this is a ground state? Let us try to change something in the state and see whether you increase or decrease energy. Since number of electrons is conserved, the only change we can do is to take an electron from field state and put it here. But as you see, this energy is higher than this one. So we pay energy for this excitation. So we go to something which is not ground state, which proves that initial guess was correct. The state with all levels below energy field and all levels above certain energy being empty is the ground state indeed. Did I manage to make it clear for you?
Yes, that's very clear.
All right. Fine. That you also know from the certain course, from a solid state physics course. There is this Fermi energy. And if you map it in the space of K, it means that all states with K smaller than Kf are occupied. So energy determines Fermi momentum, the biggest momentum which electrons can have. Fine. Let us recall nice formulas about non-interacting Fermi gas. Let me compute particle energy and energy density. I'm gonna use it for further calculations. Good, so what I have to do, right? I assume that there is certain K Fermi and immediately related to Fermi energy. Right, I wanna compute the number of electrons and total energy. So how did I do this? For any field state, I add either one or energy of the corresponding state and sum up over all field states of all K with K smaller than K Fermi. There is a factor of 2 in front of it because of spin.
Yuli, there are more questions about the previous slide in the chat.
What is the superscript of C? Okay, let's see. Yeah. Oh, okay. It has just dagger plus, and what you see is a misplaced arrow. Arrow must be here. Arrow belongs to K. K is a vector. All right? K is a vector, three-dimensional vector. Good. Then we come to the formula which we use many times in the course. It's how to get from summation over quasi-discrete spectrum to continuous spectrum. It all goes in the same way. Summation goes to integration. And there's a number of states in unit cube of K per volume. So it's proportional to the volume of the system. And there's always a kind of, not to forget, there are always these pi factors. So anytime you integrate over K, expect these factors to appear in the denominator. 3 here, it's dimension of the space we consider. For one dimension, it would be just this. Fine. Let us see what we. Oops. Let us see what we can do. Well, after that, we got volume in front of it and divided by volume. Right, then it appears to be an elementary integral, which is most efficient to solve in spherical coordinates because it depends on modulus of k only. So here I transform it to spherical coordinates. So I integrate over only of the radius in k space. All right, here's the answer. So density of electrons is proportional to kf cube, as we can figure out from dimensions. Fine. Energy is almost the same, but well, again, instead of 1, you integrate ek. And right, it's the same elementary integration, and this is the answer. So a particle in average has energy of about 60% of Fermi energy. That's energy density. All right, I hope that there were corresponding exercises in your solid state course. Usually they are. Fine, let us go further. Now I want to simultaneously, now, in exact terms, I would like to formulate a model to describe the magnetism. Right, and again, I formulate the simplest one. And I recall that magnetism is orientation of spins. And in this situation, if I look at the axis in the direction of magnetization, I plainly have more electrons with spin up than with spin down. Excess of spins. So that's what I wrote. I define a convenient letter, which is degree of polarization. Polarization is 0 if numbers of electrons with different spins are the same. And polarization is plus minus 1 if all electrons are polarized. Good. We have made a decision about this. That's what we want to have. We want to have a state which has different numbers of electrons. So how to do this? Let's do it in a simplest way. Let's assume that these electrons with different spin directions are just independent gases. And let's choose the ground state of each gas in such a way that it accommodates these numbers of particles. What does it mean? It means that Fermi energy of spin up must be bigger, and Fermi energy of spin down must be lower. Correspondingly, Kf for spin up must be bigger. Kf for spin down must be smaller. That's what I have here. So different Kfs Fermi vectors for different particles. Right, and we can write down in terms of creational operators the state. Right. Our assumption is that this is ground state. But let's see that we understand how it is organized. Well, I didn't do anything complex. I just created all electrons with spin down, filling all the states within corresponding Fermi sphere. And then I created all electrons with spin up. So I get a number state. Right. And then we come in a little bit sensitive situation. We know for sure, one can check it with the Hamiltonian, which we will have, that this state is not a true ground state. It doesn't fit Hamiltonian. It's not eigenfunction of the Hamiltonian. I will answer this question, Sebas. But we don't want to work with more complex state. What's the way to proceed? This state we just introduced has a parameter, this polarization. One can vary relative numbers of electrons with spin up and spin down. Okay. So it depends on the parameter, and correspondingly the expectation value of energy for the space state depends on the parameter. All right. Then next we just will try to, from this manifold of the states, we'll try to find the best one. The best one is one with lower energy. So we will try, we will minimize the expectation energy we calculate with respect to polarization. And we will see if polarization is energetically favorable or not. And thereby, we can see if the magnet state is eventually realized. So this is approximation. Now the question of Sebas, how does this differ from previously defined ground state? Previously, we just had same numbers of electrons with spin down and spin up. So both KFs with up and down are the same. Non-magnetic Fermi gas. What is before, you mean, Sebas? It means that plus corresponds to the first index for spins up, and for spins down, you take minus. Very good. So at least we have some program to work on, some plan. We are going to compute the energy average of the Hamiltonian for this state, for our probe state, or in other words, for trial wave function. Fine. We know already kinetic energy. I still have to establish some model for interaction, but as far as kinetic energy is concerned, we know just K squared divided by 2m per electron. Good. So how we can compute it? Just some fancy way to present it, which yeah, appears to be useful. All right. I notice that in any case, for each spin direction, number of electrons is proportional to the cube of Kf. From the other hand, energy, which we want to compute, as you can see from previous calculation, is proportional to fifth power of corresponding K vectors. And there's a plenty of coefficients coming, which I kind of don't want to keep. So I write it as follows. I estimate Kf for every direction up and down from this formula. This gives me factors 1 plus minus p, different numbers of electrons, to the power 1/3. That will be wave vectors. And okay, I put them into power 5. Good, that's what I got. I got. This is a contribution, let's see, from electrons up, and this is for electrons down. And there is a coefficient, which is just kinetic energy without polarization. Do you see how this goes? Fine. I just want to make it simpler and be able to make a quick plot. So now I plot this function. So this is polarization energy divided by energy of this wave function with polarization divided by kinetic energy without polarization. Can you repeat why is there a power of 1/3? Because we want to express Kf in terms of number of particles. So I invert this relation. I got the power of 1/3. Fine. We make this quick plot. We see that the minimum is eventually at 0. It is energetically favorable to have no polarization, right? And if you want to make polarization, it will cost you kinetic energy. Yeah, we compute how much does it cost very accurately. Good. Important, although rather obvious conclusion, there are no magnet states. There are no magnetic states if there's no interaction. So we have to think more about interaction. Let us do this. Let us recall that interaction in vacuum is column 1. This is a potential. I frankly don't like System International and fancy coefficients there. I wrote it in CGS system. In System International, I guess that has to be, actually I don't remember, something like that. I will skip this coefficient. I will write everything is in CGS system. Good, that's an encoded representation. If we want to do Fourier transformation of this potential, and if you recall how we have dealt with interaction, how we have presented it in second quantization, you also recall that it's Fourier component of potential which appears there. Fine. We have to do the Fourier components of this potential here. As you see, it diverges at small q as 1 over q squared. What does it mean? It means that potential is long-range potential. That does not really correspond to what happens in the metals, where there are many electrons at rather short distances from each other. Good. So if we consider 2 electrons in the vacuum, 1 and 2, I have to take into account that there are many other electrons around, and they screen the interaction between these 2 electrons. So this interaction becomes of a finite radius. It's multiplied with this exponent, which strongly suppressed Coulomb potential at distances bigger than this screening radius. All right. So a real interaction between 2 electrons in the metal is not Coulombian. Real interaction is screened interaction. Fine. If you do it in Fourier domain, look what I have. I've got an addition in the denominator, and this, a Fourier component, becomes finite at small q. It is finite. Let's make a simple model. Let's assume that it is the same everywhere, so that it does not depend on q. Right? That's what we have. If we go back to coordinate representation, we have the model of contact potential. So electrons do interact with each other only if they are in the same point. Good. I could perhaps run this calculation for more sophisticated model of the potential, but as I said, I want to keep everything very simple. So that's a model which we will use today. It is called contact interaction. Electrons interact only if they are in contact in the same place. Right, good. So how to write interaction Hamiltonian? Just to go to previous lecture and to get from a sort of there. You do remember there are 2 particles. Let me draw it as I did it before. 2 particles to be annihilated with k prime k, and in principle with different spins. There's interaction, and there are 2 outgoing particles with k plus, let's see, k gets q, k prime gets minus q, and spins are the same. So we've got a immediate technical problem. We want to evaluate the expectation value of this term with respect to our trial wave function. So what we have to do, it is perhaps, at least in the lectures, perhaps you have already started your homework. But at least in the lectures, it's the first time we encounter such a problem. Let me formulate general principles. How do you deal with this with these types of calculations? First of all, it's very general point. It is the same for any complex activity. Just don't panic. You can do this. So how to do this? We need to reduce the number of operators in your expression. We have 4. We want to reduce it somehow. How we can reduce the number of operators? This state is a number state. So if we work on this state with these 2 operators, what you got? It's just a number corresponding to number of electrons at certain level in front of the state. Sure, we replaced 2 operators with a number. We have reduced the number. Good. If it goes in this combination, it's fine, but sometimes it doesn't want to come in this order. So we need to commute operators in order to be able to apply this formula. Well, that's also doable, right? We know the commutation, anti-commutation relations for these operators. And as have mentioned already, many answers in quantum mechanics, in advanced quantum mechanics, are just 0, which means that many terms in this expression are 0 indeed, and one has to use common sense in order not to compute zeros all the time. So looking at this expression, one has to understand which terms do not give 0 answer. Okay, with this, let me compute this combination. This K1, K2, K3, K4, they just corresponding levels. Just a second. There's a big disturbance at my home. They shut down electricity in my region of the city. So there are all possible problems related to this. I'm sorry. Good. So about these computations. 4 operators, creation relation operators with generally 4 different indices. All right, let us use the last rule and common sense. You have some numbers of electrons, then you create 2 and you annihilate 2. If you create in in the states which differ from the states where you annihilate, you never got the same occupation numbers for the whole state. So occupation numbers must match. Each creation must be compensated by annihilation in the same level. Good. That's point clear. We don't want to compute zeros. So we need to somehow couple creations and annihilations so that they correspond to the same level. And we notice that we can do this in two ways. So let me just finish this calculation before the break. In two ways. Those are indicated here with arrows. There is a red way and blue way. So there are two possibilities to associate annihilation and creation. Good. Let us try red way first. So I will rewrite it, taking correspondence between these levels, taking correspondence with these equalities. Good. I cannot immediately apply this reduction formula. Okay. I want to compute. Here, I have commuted. Why do I do so? I want that C dagger comes closer to C. All right, so I have commuted this two. I got minus sign. Because anti-communication, I have assumed that K1 is not K2 in order to do so. Right, then I can immediately apply this formula. Hop, this gives me factor NK2. This is left, hop, it gives me a factor NK1. Right, for blue web. I have to commute twice before I got C and C dagger in proper order. Then it's just the same factors coming, but with minus sign. All right, this is calculation, which looked difficult, but well, with some effort, it can be done. In fact, it is simple. Right, let's have a break of 7 minutes. So we are back at 9:40, and I switch off the recording. Where we are now? Do you remember? We have computed this long expression involving 4 operators. Some of them have already did it in your homework. Let me remind you about homework. Fine, now we need to sum up it, right? Because the Hamiltonian, which we use, interaction Hamiltonian, needs to, condense many terms. We have to sum up all of them. These two ways to connect operators kind of got very honored by assigning them names of different scientists. So let me talk first about Fermi Energy. And here I connect operators in this way. And as I see, I connected with the same spin. How can I picture this? Well, I start again from the term, where there are two incoming particles, two outgoing particles. And now I close these lines. I close these lines to take into account that this state and this state are the same. All right, so I have two closed loops connected by interaction line. If you wish, it's Feynman diagram. Good. Now I can apply the results. So what I get are occupation numbers. And I need to sum up over K and K prime, which is particularly simple in this example. Perhaps you may recall what Miriam told you last time about double sums. So there is a sum over K and K prime. But if you look carefully, please look carefully, you understand that this is just square of a single sum. And we know the sum is just full number of particles. Okay, so we get this energy. It's called Hartree energy. Right. That's what I get from calculation. Well, I'd better write down it in terms of density, electron density, small m, to make it obvious that the energy is proportional to the volume. All right. That we computed, and we can already draw a simple conclusion. Polarization here doesn't matter whatsoever. The answer depends only on total number of electrons, whatever the spin. That seems logical, so perhaps interaction doesn't depend on spin at all. Well, it is clearly not so, because otherwise I wouldn't have this story. So let me try another term. Let me try another connection of creation and annihilation operators. Good, so I connected in the right way. And remember, I got minus sign in my calculation. But what is more important is that it actually sets all spins to the same value, right? So here spins are the same per definition. If one makes this connection, right? So one needs, the only way to close this line is the way I've shown, right? And the spin along electron line is the same. Fine. So that's what we have. That's what we want to sum up. Very simplified, assumption which we made, that potential doesn't depend on Q, just constant. With this can be seen as a sum of squares of total number of particles for different spins. So that's we got. Again, this is double sum, but this double sum is separate for two separate spin directions, and we have to sum up our spin directions. Good, so it's minus sign. It's number of particles with different spin, and now we have dependence on the polarization, minus sign. So that we have finally identified the possible origin of magnetic state, because we see that hot energy eventually favors the polarization. Hot energy is smaller for magnetic state. Good. So now we can step by step to the total energy, which includes kinetic part and potential part. So here I have two coefficients: initial kinetic energy and hot energy. And the actual answer depends on the ratio of the two. So if the ratio is small, no interaction, of course, the state is non-magnetic because polarization costs kinetic energy. And it turns out that it stays non-magnetic till some critical value of this ratio, which is 10 to 9, right? Then finite magnetization appears. And at some other critical value of this ratio, all electrons just turn to the same direction. Polarization is absolute. Magnetization is saturated. So how can I come to this conclusion? Well, more or less, I'm just making plots of this expression. Right, so I have three contributions, two contributions: kinetic energy, potential energy, and the total energy. And I see where do I have the minimum of total energy. This is kind of a mathematical equation for the minimum. Fine. We solve the problem. We have found magnetic state for a certain region of parameters. Well, to which extent the model is realistic, it's of course a question. One can sophisticate it, one can take into account all different peculiarities of interaction, of the spectrum, so on, so that it's not clear to which extent it is applied. It is clear that it cannot be immediately applied to any realistic metal, but there are ways to make it more realistic, looking at concrete metal, applying computing direction, computing spectrum. Fine. So we have a new vacuum, which is the same in this region of parameter as an old one, but here it's certainly new. It is magnetized. I will concentrate on this particular region when polarization is not absolute. Not all electrons are polarized in the same direction. It's also more realistic. In the most magnetic metals, you find electron spins of both directions. Right, there was a question, how does this model compare to, for example, the Heisenberg model? It cannot be compared at all. It is, if you wish, an alternative model of magnet. So how does this alternatives come about? Heisenberg model works more for insulators. Heisenberg model assumes that there are atoms, localized states, and there's a localized electron at each atom. And there is a small interaction between spins, which comes about the tunneling of electrons between these two localized states under high interaction. So it's more or less insulator model. We start with opposite limit, with metallic limit, where all electrons are eventually delocalized, or plane waves, in distinction from starting point of Heisenberg model. But we got similar results, thus polarization at some choice of parameters. Serkan, does it answer your question? Good. Let us see. So we got ground state in our hands, and we would first we notice one important thing, but spontaneous polarization, spontaneous symmetry breaking. We have chosen some quantization axis for our calculation, but this is eventually a direction in three-dimensional space of spin, and it can be arbitrary. So if you got magnetic state, it's not a single one. It's a manifold of all magnetic states which differ by the direction of polarization. All the states have the same energy. Right, so popular illustration for spontaneous symmetry breaking is a bottom of wine bottle. So let us see, let's have wine bottle. Let us recall how bottom looks like. So it could have been symmetric, this ground state in a wine bottle. It is not. Well, because, you know, there's a potential maximum right in the center. So if you put a particle into the wine bottle, it can be here, but it can be also here or here. So this is an example of spontaneous symmetry breaking. I'm not sure about beer. Never checked this beer, but for a wine bottle, it certainly works. Good. So how does it apply to our case? All right. Rotational symmetry in three-dimensional spin space is broken. Also, since we have magnetic field, we also have broken time reversal symmetry. Right, magnetic field means that time reversal symmetry is broken. Why? Magnetic field is due to currents. If you reverse time, all currents go to opposite direction. Magnetic field will flip the sign. Good, and I'm gonna formulate a very interesting rule which describes a creation of new particles, right? That has been proposed by Goldstone, whatever was noticed by Goldstone, if you have such continuously broken symmetry, you can change the state, paying very little energy for that. And that means that you have new particles with low energy, which kind of reflect this effect, the continuous symmetry breaking. So this implies that for our vacuum, since the symmetry is broken, excitations must be interesting. So let us investigate the excitations. But I don't want to jump immediately to interesting stuff. Let us first see what we can say about usual excitations. Right, first of all, excitations in a metal. No polarization yet. Good. Ground state can be seen as a vacuum for our metal. Let's get some excitation. So what we can do, again, advanced quantum mechanics usually about doing, although it seems pretty mathematical. We just create excitation and see if it fits. What we can do, we can add an electron to this ground state, making an electron excited state, a state with single excited electron. So that only works if there's empty space to create this electron. So that only works for K, which are bigger than KF. Another possibility is to extract an electron, is to make a hole in field states. So that works only if K is smaller than KF, and it defines a hole state. I have reverted signs of momentum and spin for the hole, because the hole is just absence of electron. Okay? So this momentum K and spin sigma are extracted. They come with minus sign. Both excitations have positive energy, well, that you can see from this plot. Good, so I have two kinds of excitations, two branches of spectrum, electron branch and hole branch. They're separated in K space. Fine. Let me now do the same for our model, for our ground state, which we have found. The picture gets a bit complex, but still we can easily comprehend it. First of all, how to compute that? In any case, we are working with number states. If we create or annihilate an electron, we just got with the same expressions which we have computed. Now we need to compute the differences of energies corresponding to addition of an electron and instruction of electron. That has kinetic part, but that also has something coming from the interaction, change of interaction. And that splits the energies of the excitations. It has to be true because we assume that the KF, K vectors are not the same. So the splitting is eventually related to the difference of K Fermis for two different spin species. Good. So I need to replot the same plot with split levels. So I have two electron branches with different spins here and here, and two whole branches. I see that now they all can also overlap in K space in this interval of Ks. I could have simultaneously electron and hole excitations with the same energy, which have spin down. Pay attention to the fact that the spin of the hole is opposite. It's electron extraction. All right. Again, it's easy computation, and we just use the fact that we again create number states which belong to the basis of artifact space, which are characterized by a set of occupation numbers for each level. Why should the K be lower than Kf for electrons? I thought it should be higher, such as in place. Let see. Oh, okay. Sorry, you're right. That has to be opposite here. Oh, I need to correct the transparency. Here. It has to be opposite. Fine. Other questions? Good. It's also single particle excitations. I want to make another simple story because I want to talk about electron-hole pairs. But electrons and holes are charged excitations. One has to really bring the charge to the metal or extract the charge. Let's see what we can do within the metal. Well, this is what we can do. We can create electron-hole state, which actually means that we have transferred an electron from filled state to an empty state with different spin directions. Let us see. That's how I write it. I choose it in such a way that the total momentum is the same, but there's also a difference of momentum between electrons and holes, right? And if these operators work on this state, they shouldn't give zero. And that I have taken into account with this factor. So the state with K minus Q has to be filled. The state with K plus Q has to be empty. And that also depends on spin under our circumstances. Well, what would be the energy of the state? Nothing fancy. It's just sum. It's just the sum of electrons and holes, right? Kind of we create these electrons and holes. They're not related. They just go far from each other. They don't interact. So the total energy of this excitation is the sum of electron and hole energies. Here, what I put here, let's see, I'm doing the spectral time. Oh, there's still some time. All right, that's what I got in the answer. Why did I take care of all this algebra? Because I want to make some plots, and I want to indicate that the answer also depends on spins in our new vacuum, in our magnetic state. Right, so this energy, and let's see what I do. I plotted it versus Q, but I plotted for all possible case, right? So I don't have a line over here. I have many, many lines for all possible case. So in fact, I fill up the whole region with the spectrum. Good. So let me see. There are different spin configurations. Both electrons down, both electrons, both spins up, both spins down. In this case, one can create excitations with very low energy near Fermi surfaces like you do in the metal. There are special cases of opposite spins, right? It means that the total spin of the system has been changed. All right. If we add spin, well, we have a difficulty to that. We cannot add spin till certain Q. If we extract spin, we can do so, but there is energy gap to do it with zero momentum. So in fact, and this is rather important to for what I will say later, there is a gap for excitations with the spin configuration. And if you create this configuration, you extract spin 1 from the magnet, or in other words, you turn one of the spins down. All right, so it's obvious one that can go further. One can consider excitations with 3 electrons, 1 hole, with 2 electrons, 2 holes. Will be rather boring job. One can do this. So one can do this. And now I'm about to tell you about. I'm about to tell you an alternative, which looks fancy, but it's more or less what Goldstone has proposed to describe low energy excitations which come about the spontaneous symmetry breaking. Okay. Let us see. Let me take one of the ground states I just created for you, which looks in a certain direction, say Z direction. And let me rotate it in spin. Now we need to recall a little bit about spin and momentum. You got it at quantum quantum mechanics at some stage. I didn't refresh it, but I assume you know this. Operator of rotation is eventually operator of spin, operator of total spin. Good, I'm gonna rotate in X direction. I'm gonna take X component of the spin. So in that direction, I rotate it about that axis. And if rotation angle doesn't depend on a point in my metal, I'm doing pretty boring thing. I'm gonna get this equivalent state which is precisely the same energy. Let's try something else. And let us assume that this angle is varying in space slowly. Varying slowly is the limit of constant. So we kind of have an idea that the resulting state will be also low in energy. Let us see. This is only true in a symmetric situation, all right? For example, this is no longer true if we apply an external magnetic field. If you apply external magnetic field, you got some extra energy related to orientation of magnetization with respect to spin. But it does not deny there's still some energy profile which permits you to have the spontaneous symmetry breaking. Let me get it practical. Let me recall wine bottle. Is this potential profile. Okay. And if I apply magnetic field, I kind of tilt it slightly. Okay. So there's some energy associated with tilt. So now ground state is really here, but it costs only a small energy to get here as well. Much smaller than to get to the maximum. All right, Sarah, does this answer your question? So one can still rotate.
No, but that energy to get onto the other side is no longer zero. So there's first order state transition, which breaks the global symmetry as well, right? If you apply magnetic field.
One can say so, but if you apply a small magnetic field, the corresponding energy will be small. If it is small, one also has to take into account that there is a potential minimum like this. Right? If you tilt your wine bottle by 45 degrees, you can perhaps forget about this. But if you tilt it only slightly, you have to keep into account the fact that there can be rotation around the bottle axis. Good. Let me go on with calculation. So the trick is to make this angle slightly depending on coordinates. Good. If it changes quickly, then perhaps I have high energy. If it changes smoothly its approximation to a constant, I expect small energies for the resulting state. Right. And the exponent is too difficult for me. I'd rather expand in terms of small angle. And I take certain Fourier component of alpha, so it will be in this form. Plus complex conjugated, of course. In this way, in fact, I make sure that I create a particle with certain quasi-momentum q. Right? So I expand the resulting state. This is addition to this state. Addition proportional to alpha. And I just look, what do I have here? Well, I have this operators as field operators as depending on R. I go to K space, rewrite it here, keep the same K. So finally, oops. Finally, I come to this expression. This is deviation of wave function. And that corresponds to an excitation at small energy. Let me look close at this expression. And let me make a connection to what we know already. We need to normalize the state. Right? We need to normalize the state to bring certain normalization factor. This is this normalization factor computed. But most important point, what we have here. So we have sum over K of this combination over certain Q. But if we go 2 slides back, we recognize that each term creates an electron-hole pair. So in fact, we have created an electron-hole pair, but it is in a superposition of all possible states which differ in K. Equal weights superpositions. So all coefficients here are 1 or 0. That's the magnet. We have here, in fact, an operator of the new particle, creation operator of a new particle. Good. Let's investigate what for particles are there. And to this extent, I can check commutation relations. I can check commutation relations. I just substituted here the commutation. And that's what I got. Well, it is still an operator, which presumes that perhaps I didn't get very exact expression for Magnan operator. Perhaps I have some small mistake somewhere, but this mistake is small because if I replace these operators by their expectation values in the ground state, which means I consider magnets only close to the ground state, I just got one. So what I have proven now that magnets are bosons. We have a new a new particles, new branch of excitation spectrum at low energies, and this is bosons. Although we didn't have any bosons originally, we had only electrons. Fine. Let me show you boson spectrum. Okay. I also can want to make a couple of remarks how to compute the spectrum. No rocket scientists, just something operation. So to compute the Magnum spectrum at a fixed Q, you just assume a wave function. You assume a wave function which is a superposition of electron-hole pairs. You put this into Hamiltonian, and it says that Hamiltonian has non-diagonal matrix elements within this wave function set. All right, you write this non-diagonal matrix elements as a matrix. So in fact, you're kind of again find the best approximation for this trial wave function. Good. Then you have a kind of Schrödinger equation for this wave function psi. You solve this. You solve this equation. You find eigen energies corresponding to this solution. You're done with the spectrum. Good. So I plotted the results for you. What's my say? At the full Magnum spectrum at all possible K, which also can be compared with KF. You remember this, there was a continuum of electron-hole pair spectrum. It is here present as well. I got it in the previous picture. And the Magnum branch is within the energy gap. At small k, energy goes to 0. The spectrum is parabolic. And you see that parabolic approximation actually works pretty well through the whole region. It's only near continuum. Somehow it wiggles near continuum and merges with continuum at some point. Right, magnons. And that's it. So let me sorry, I don't have something. Okay, let me summarize it. So we have started today with examples of condensed matter systems. The reason for that it's just interesting with each new condensed matter system, we have a new universe, new vacuum, new excitation, the whole universe to explore. And we did it for magnets. We have found simple trial wave function, and with minimum of computations, we were able to establish that this magnetic ground state is a true ground state. Right? Then we look at the excitations. There are usual electron hole excitations, which are split in spin. And due to broken symmetry, due to rotational symmetry, we have discovered, not us, but we have discovered magnons. We have discovered new particles arising in this symmetry broken vacuum. All right, that concludes my lecture. Let me stop the recording.